Hello everyone and welcome to this brand new lecture series on the simulation of electrical machines. So last week I concluded on the video series which was based on DC to DC converters, and I finished simulating the forward converter. So since we are pretty much done with DC to DC converters, of course there are many more converters, but I've covered most of the major ones. It seems sensible to pick another topic. So the topic I chose is simulation of electrical machines, especially with the dynamics of it associated as well. So to begin with, let me just go over to my website, which is pythonpowerelectronics.com. So this is the home page of the website. Feel free to check it out. There are several links. You can go to the learn button. These are all the different courses I have on different topics in power electronics. Most of the courses are hosted on Udemy, and they are hosted usually on how to simulate circuits using Python. Some of them are also related to basics of digital signal processing and also on control. And besides this, you can download the different versions of the circuit simulator, Python Power Electronics. So you see these are all the different versions. There are two different types of this. The circuit simulator rather is available in two different types. One is a web app and the other is a command line. And these are the latest versions of each of them. Unless you are very well versed with command line, or if you're a Linux user, I would recommend you to use the web app, because the command line does require some knowledge of Unix commands such as running circuits, running Python scripts, and also how to plot using GNUplot. Whereas the web app has almost everything. So the recommended form is to use the web app, and I'll be using it here as well. Besides this, you can go to watch. This is the collection of YouTube playlists which I currently have. There is a playlist on how to install the circuit simulator. This is the lecture series which I concluded last time, which was on simulating DC to DC converters. And there are some others, such as this is on basic Python, on the basics of Python, as well as on data science. And there are a few others as well, right? So feel free to check them out. And besides this, I also write books and have released some papers which you can also read. So these are basically just papers which are more or less white papers on different aspects of circuit simulation. So go ahead and check them out. So these are different things. Go ahead and go through the site. I've tried to make it as animated and interactive as possible. But what is most important is I'm going to download the circuit simulator. So I've already done this in the previous versions, but in case I'll do it just again. So this web app is available as a .zip file or a tar.gz file. Either of these will do. Unless you're a Unix or a Mac OS user, it is much more convenient to deal with .zip files. So I'll download this .zip file. And let me create a new directory. So I am now in documents. Feel free to connect it wherever you want, but I would connect. These are all the different folders which I have for either courses or for different kinds of series. For example, this energy series is the series which I used before for simulating DC to DC converters. So let me just create a new one, and I will call this machine series. And within this, let me save it. So let me go to my file browser and let me choose the machine series and extract it. So I have this folder, right? So in this folder, there is the requirements.txt file and there is a simulator interface. If you're completely new to this, that is new to how to install in installing Python or on using the circuit simulator, check out the next few videos in this playlist which are dedicated towards installing Python and setting up the circuit simulator. In this video, I'm going to assume that you know it. If you're not sure, just check out those videos before you continue with this. So I already have an environment in Anaconda. And this is the one which I usually use, that is CircuitSim. I have several others which I use for various purposes, but CircuitSim is what I usually use. So let me activate it. And once it appears in the parentheses, it means it is active. Let me clear the screen and let me go into my documents folder. And let me go again into machine series and into web app. Again, as I said, if you're completely new to Python, then in that case, you should check out the other videos on how to install Python and how to set up the circuit simulator. I do not need to do it because this is already a working environment, right? So I'm going to go directly to setting up the simulator for this particular project. You can use one simulator for multiple projects, but just in case, I would like to keep this separate so that I have my simulations in different databases. You don't have to, you can have it in one place, but this is just for my own convenience. So the first thing I need to do is I need to do make migrations so that it creates the tables. So all I have to say is make migrations simulations. And as you can see, it creates all the different tables. These are all the tables for each and every electrical component. And after this, I need to migrate because this has created the tables, but I need to write those tables to the database. And this is exactly that. So you see here, the last line says this, that it has written all the tables for simulations. So we are now good to go. So I can now launch my circuit simulator. Right? It is available at this link. So let me open it. And go to a web browser. The recommended web browser I would use is always Google Chrome. But again, there's no hard and fast rule. You can use just about anything. It could be Internet Explorer, it could be Mozilla Firefox, any of them, right? They're all the same. So most of the pages have some instructions, and you'll see that there is no simulation library because we just installed it, right? So let's create a new simulation. Now, the purpose of this entire video series is to simulate electrical machines. So to get started, I'm going to simulate a simple resistive inductive load that can be made to behave like an electrical machine, such as an induction motor, right? So let me call this sample RL load. And let me copy and paste it here as well. And if you've used it before, you know how this works. The time duration can be 1 second. This is for how long you want the simulation to run. The integration time step is the time step at which you want to solve your differential equations. It is recommended to keep this as small as possible, right? For most regular power electronic circuits, 1 microsecond is good enough. If it is a high frequency power electronic circuit, such as a flyback converter or a resonant converter, this would have to decrease to a much smaller value. You might have to go as small as 1 nanosecond or even smaller than that if you're having like a high frequency resonant converter, right? If you have a 500 kilohertz resonant converter, this might have to be 1 picosecond, right? The time step of data storage is the time step at which you're storing the data, right? Now, this has to be greater than the integrations time step, but it can be equal as well. I would keep it equal so that I have a good accuracy with respect to my plots. And the name of the output data file can remain as it is unless you want to separately plot it using matplotlib. But for most purposes, the plotting which is available with this web browser, web application is usually good enough. Slicing the output again is not really necessary unless you're using your own plotting functions. And if this is known, number of slices doesn't matter. So now comes the directory. So let's go over. And now within this machine series, let's create a new directory. We'll call this simulations. So this is where we will store all the simulations for this entire video series. So within this, let me now create another folder. Let me call this simple RL load, right? And within this, let me go and create a very simple circuit. So I'm going to call this wire, and let me quickly pull this and create a skeletal framework. So let me just pull this through and create a branch this way. So there'll be a voltage source here, there'll be a resistive inductive load here, and there'll be a voltmeter here to measure the voltage across it, right? So I will call this voltage source, let's call it Vin, and let me give this a parasitic resistance and call it Vin. It can be the same name because they're different components. And let me give it an ammeter. Let me call it Vin also. This is just measuring the current supplied by the voltage source. And here let us call it resistor, load, and inductor load. And just for the sake of it, let us also measure the current. In this particular circuit, we probably don't need to measure the current because the voltmeter will not draw anything and all the current will pass through the load, or at least a significant amount of it. But just for the sake of it, let us create an have an ammeter in both places. So this is a very basic circuit, right? Simple single phase voltage source connected to an RL load and measuring the voltage across it. This RL load can symbolize any kind of load, right? So for example, I'm just going to go and save as. Now let me choose machine series, simulations, simple RL load, and here most important, go to formats and choose text.csv, right? Do not save it as the default value. It will save it as an ODF spreadsheet. If you're using Linux, in Microsoft Windows, you will have to choose MS-DOS CSV, right? Do not save by default XLS. It will not save it. You must save it as a .csv file, which is a comma separated value file. In MS-DOS, in Microsoft Excel, choose MS-DOS CSV, right? And let me just give this a name. I'll just call it RL load. It'll ask you for this. It'll just say that these are the documents. The field limiter should be a comma. Do not choose a semicolon. Do not choose any of the others. Keep it as a comma. The text delimiter can be a double quote, can be a single quote, doesn't really matter. You can leave it anyway. And the rest, you just leave it as default options, right? So we now have our file. So I'm just going to close it. Go to the file browser and open it again, just to make sure that it has been saved successfully. And yes, it does appear. So this is now our file. So what we're going to do, go to the file browser and check the properties. In the properties, you'll see the parent folder. This is the folder which we need to copy and paste it in our directory. This is the working directory which contains all the circuit files and where all other files generated by the circuit simulator will be stored, right? Make sure that you have full write permissions and read permissions from this directory. If you are logging in as an administrator in your account, do not choose a directory which is protected. If the circuit simulator cannot write to it or cannot read to it, this will not work, right? So save the parameters. If you see this screen listing out the parameters, in that case, it has been successful. And if you go to the file browser, you will see that there is a test file written. It is a 0-byte file. It's just a blank file for the circuit simulator to test whether this directory has write permissions, right? So with this, let's go back and now we can start adding the circuit file. So we've created a circuit file. We can add it. Go back to simulations, documents. The new one, machine series, simple RL load, and let us choose the CSV file. Let me call this RL load. Save it. So make sure that the file appears here after you click on save. If there is a blank form, don't worry, it doesn't matter. Nothing happens as long as you save it and it appears here, right? Whichever circuit you add, you must click on the save button. It must appear here in this list, right? So after adding it, you must click on process circuit schematics always, right? The process circuit schematics checks if there are any errors in the circuit, and it also creates components for each and every, or rather it creates Python objects for each and every electrical component in your circuit, right? So if there are no errors, you can go back and we can go to edit circuit parameters, right? So here we can start editing them. So there are a few changes. You just have to check what are the parameters of the circuit. For example, the ammeter is at 1B pointing to 1C. If you come over here, you see it means at 1B. The direction, the positive direction is towards the right, and that's perfectly okay. This ammeter is at position 4E and the positive direction is 3E, which means that direction is upwards. Since it is a load, it makes sense if the direction is downwards because it will draw a current. So let's go change that. So I'll make it 5E. And the inductor. Now the inductor, we can just choose a random value. Let's make it 0.1 because you want a fairly, actually you can make it even larger, like 0.2 or 0.3. Doesn't matter for now. I'll tell you why later. The resistor Vin, make sure which resistor it is. Vin is the parasitic resistance. It is this one, right? This parasitic resistance is a negligible feeder impedance of this voltage source, which means it has to be very small. It should not be 100 ohms. The default is 100 ohms. That's way too big. So let's reduce it. The resistive load, this is also 100 ohms, can be reduced but not to the same limit. We have to reduce it to something like around 10 ohms, right? Because it is a load after all. And if it's a load, you want it to draw some significant amount of current, as long as it's not a short circuit current. Then comes the voltage source. Now, the voltage source depends on where you are. If you're in North America, this can be around 170 volts, 60 hertz, right? Because in North America, the RMS voltage is 120 volts, 60 hertz, right? And if the RMS value is 120 volts, the peak is around 169.7, right? So you can approximate it to 0.70 or you can leave it at 169.7. Now, I am in Germany, where the voltage is around 240 volts RMS, which means it is a peak of 339 volts, right? And the frequency is 50 hertz, right? So unless you're in US, Canada, this is pretty much the voltage you'll be having at your single phase output, right? So this is what I will choose. The component position is at 9E, positive polarity is 8A, which means it is upwards, right? And that's perfectly okay. So with this, I'm going to save it. And here, the voltmeter. Since we have a 240 volt system, which means a peak of 340 volts, a rated voltage of 120 volts is too low, right? I would choose it to be larger. The only thumb rule is choose it to be much larger than the voltage that you expect in your circuit. There is no hard and fast rule. This is not a real circuit. This is just for the internal solver to make sure that the voltage of, or rather the resistance of the voltmeter is large enough that it does not disturb the circuit. That is all that matters, right? So make this larger. You can even make it 10,000 ohms, 10,000 volts or 5,000 volts, whichever. As long as it's not 10 volts, right? If it is 10 volts or 1 volt, you might end up with calculation problems. So do not choose something too small. Now, the component position is at 8H, positive polarity is at 7H. And that means the positive polarity is upwards. And that's perfectly okay because the voltage source also has a positive polarity upwards. So with this, save parameters, and we are done. So let me go, and we don't need a control file because as of now we are not doing any control. All we have to do is run the simulation. It says simulation is running. Now in this case it probably is running, but always when you click the button, even if you see this message, go to the command line and check if there is any error. This becomes important when we start writing control files. When you write a control file, you will find that sometimes if there's an error in your control file, which could be a Python syntax error or it could be anything else, those errors will appear here in the command line and you will not see them in the web browser. So always when you click on the start button, always go and check if there's an error. So with this, we can just plot it. Now what do we have as a plot? We have the current and the voltage. So let's go plot these two. So I'm just going to click on add plot. I will just call it voltage. Start the plot. Select the voltmeter load, call it V. Save the waveform. Click on done. Right? So make sure that this plot appears. Make sure that there is a signal which is added and that is being assigned to a variable. I'll just add it again and I will call this current and start the plot. We can add two of them. So we can add ammeter Vn, which is the input current. So I'll call this I1. Save the waveform. And we can also add the load current, call it I2. These two should be almost equal because the voltmeter is going to draw a negligible current. But let's just plot it just for the sake of it. Click on done. So we now have two plots. So let's create those plots. So I'm going to plot it and plot this one as well. So this usually means that it's actually generating the plot. So just wait for it. When it jumps up like this, it means the plot is done. So let's go over and click. So now this is our voltage. And you see this is indeed the voltage. We have a peak of around 340 volts. If you want, we can zoom in. So let's zoom in between 0.5 and 0.6. And let's just check out the current ones. The current is also pretty much sinusoidal, or at least looks like it. It has a peak of around less than 4 amperes, and it seems also sinusoidal. So let's just zoom in. As I said, let's pick 0.5 to 0.6. Doesn't matter, you can pick anything you want. Actually, we can't do two together, so just one. You can only generate one plot at a time. And we'll have to write this again. So let's click on the voltage and you see that this is indeed a sinusoidal voltage. And a sinusoidal voltage with a peak of around 340 volts, right? We can zoom in even further, but let me not do that. I will leave this to you as an exercise if you want to examine this further. And if you see, the time period is indeed 20 milliseconds, which corresponds to 50 Hertz. So if you look at the current, also sinusoidal and seems like a pure AC waveform. The DC offset is because of the inrush current because of the very large inductor, right? So with this, we now seem to have a working RL load. Now the question is, why did I want to do this? The reason I wanted to do this is that even this basic RL load, right, is a very, very crude way of modeling a particular load, right? Even if you have an induction motor or something and you want very, very quickly to know what kind of current it draws, it is possible to choose a resistance and an inductance such that at least you can check out what kind of current it draws with respect to a particular voltage, right? Now the question is, here we've chosen a fixed resistor and a fixed inductor, right? What if we want to vary this according to a power? That is also possible, and this is something that we'll do in the next lecture. Where we are getting to gradually is that we can now we want to replace this branch with a machine. That's where we are getting to, gradually, bit by bit. This machine can be anything we want. It can be an induction motor, can be a DC motor. Well, it can't be a DC motor if it's an AC source. It has to be an induction motor, or it has to be a synchronous motor, or if this is a DC source, it can be a DC motor. Or if this is a three-phase AC source, it can be a three-phase induction motor or a three-phase synchronous motor. Alright, and if you are also interested, you can also go and simulate some of the more advanced machines like switch reluctance motors and several others. Right? Again, all this will happen bit by bit. First thing we need to understand is what is the purpose of how you model any particular machine or load. The very first step is you can just choose a resistor and inductor. That's it. The next step is to vary this resistor and inductor such that you can kind of bring in some amount of variability into your load rather than just have a fixed resistor and a fixed inductor, right? beyond that, we want to then start bringing in dynamics into your system. That is, you want to know exactly how your machine behaves when it is starting up, when it is slowing down, how does it behave when a particular voltage is applied to the machine. These are what are useful when you want to model the exact characteristics of your machine, right? So this is where we are going to gradually, bit by bit. This is just a very first video just to get you started. Again, if you're new to Python and you're new to Python Power Electronics, check out the next couple of videos or the previous 2 videos, whichever it is. There will be videos on how to install Anaconda in Windows, in Linux, how to set up Python Power Electronics in Windows and Linux. So please do check out those videos in case what I have done here may have seemed a little too fast, right? And if you want practice with how to simulate in Python Power Electronics, check out my YouTube video, which is this one, YouTube video series. Just go to watch. Check out any of these video series. Most importantly, check out this DC to DC converter lecture series. In this I have simulated several DC to DC converters, and you can watch this and get some practice, right? So this video series is how to install the circuit simulator, right? A couple of videos have been included in this playlist, but this entire playlist describes in detail how to install Python Power Electronics. Whether you have Windows, whether you have Linux or Mac OS, you can use Python Power Electronics in any operating system. So if you're completely new, first watch these videos and then check out this DC to DC converter series to get some practice, and then maybe come back and watch this video series. So if you have any doubts, please do post either in the comments or email me or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will keep going with this particular video. Thank you so much and see you soon. Goodbye for now.